Okay, so we just looked at the elastic collision case, and you saw that they bounced off. The individual momenta of the two objects changed, but the total momentum of the combined system of these two objects stayed the same. It stayed at minus 0.80 kilograms times meters per second. Well, now I'm going to put this all the way down on inelastic, which means they're going to stick together. And I'll run the simulation again, and let's check this out. So now they go off together, and I'll just pause this for a second and have a look. So now both of them have combined. They've become a single object of mass 2 kilograms, right? They've united here. Their combined mass is moving at negative 0.4, and if you multiply the 2 kilograms by negative 0.4 meters per second, you're going to get negative 0.8. And you'll see here that the total momentum, again, did not change. Let's bring that back. So just, you can watch the total momentum here. So off they go, and then boom. So the two of them unite. The total momentum does not change. You can change these initial conditions. I can put the elasticity anywhere I like. So now here, what would happen is they would kind of stick together momentarily. Okay, now this doesn't want to go back to where it was. They could stick together momentarily, and then they will separate. So here's a partially elastic collision. So it's kind of hard to see what happened. But regardless, here you see the total momentum. Let me make that a little bit more dramatic. So here's the total momentum now is right here. And I can let them smack off each other. And again, the moment of the individual objects changes, but the total momentum does not. So before, 0.96 and negative 0.6, that's the individual momenta. Add them together, you get 0.36 kilograms times meters per second. Let them smack into each other, and afterwards, it's still 0.36 kilograms times meters per second. So what this illustrates is that whether the collision is elastic, inelastic, or somewhere in between, the total momentum before the collision and the total momentum after the collision will be the same. So that gives us equations where you could say, like, for any kind of interaction between two objects, well, any number of objects really, the total momentum before the interaction will equal the total momentum after the interaction. This is a universal law. It works for everything, and it's never violated. It's only when you start bringing in kind of like third parties, like the Earth or walls or whatever, that, because these things, then you had to kind of calculate them into the system. But here we just have two objects not interacting with anything else, and their behavior will always conserve the momentum that they had before.